Okay, talking about linear transformations. Okay, I didn't write the word down here, but it's worth writing down, so. Well, I didn't get to finish the word, but here it is, linear transformations. Okay, let T of V1, V2 be defined as, and this is T applied to the ordered pair V1, V2, and this ordered pair can be regarded as a vector in R2 if we wish, and I pretty much wish that. Then T applied to V1, V2 gives you another ordered pair. And the ordered pair is a linear combination of the numbers V1, V2, the components of this V vector. It's your first component. Your second component is another linear combination of the components of V. So it's a simple map. We can easily apply it. And there's a W. We'll get to that in a minute. But let's let V be 2, -3, the ordered pair 2, -3. If you wish, the vector 2, -3. So a vector in this direction in standard R2. Let me go ahead and put this camera where it belongs. Okay. So we apply the transformation. T of V1, V2 equals, well, V1 is 2, so we have 2A. V2 is -3, so we have -3B. And similarly, we're going to have 2C minus 3D. Now, depending on the values of A and B, the result here could be any vector at all in the plane. In other words, if I want this vector to equal 7, -42, well, I put 2A minus 3B equal to 7, 2C minus 3D equal to -42. I have two simultaneous equations, and I can easily solve those equations. Okay, if I know my numbers A, B, C, and D, or if I can determine numbers A, B, C, and D that'll give me that result. Okay, well, we're going to get to that. So that's the purpose of our W vector. Okay, so we have this ordered pair. Now I can also write this ordered pair as the matrix 2, and I've got the wrong numbers here. Okay, I can write these numbers, or I can write this ordered pair as a matrix equation if I regard this ordered pair as a column vector. This would be the matrix equation A, B, C, D multiplied by 2, -3. And maybe I shouldn't use an equal sign there, so I'm going to take the equal sign away. And I'll just say, make a note of the fact that these same components can be obtained from a matrix equation, because this matrix equation gives us 2A minus 3B and 2C minus 3D. We'll talk more about this matrix equation later. Okay, now suppose we want to solve the equation T of V1, V2 equals our W vector. Okay, so let's say we want to solve this equals, well, I said something, I forget what it was, 7, negative 42, let's say. Okay, so this is a matrix equation. T of V1, V2 equals W. Which equals the ordered pair W1, W2, where now W1 is 7, W2 is negative 42. If I write out the equation, and I'm going to go ahead and use, well, no, I'm going to go ahead and write it this way. Okay, so T of V1, V2 is AV1 plus BV2, C V1 plus D V2 equals negative 42. So we get a system of equations AV1 plus BV2 equals 7. CV1 plus DV2 equals negative 42. This is a system we can easily solve for V1 and V2 because we have two simultaneous equations in the unknowns V1 and V2. Now our solution, depending on the values of A, B, C, and D, might be degenerate. In other words, this side and this side might be multiples of one another. Okay, and it's very possible that this side and this side are multiples of one another, but these two sides are not the same multiple of one another, in which case we get no solution. We could get a solution where each equation is a multiple of the other, in which case we'd have one free variable, we'd have essentially a line of solutions. We'll get to that. So anything can happen over here. We don't know what A, B, C, and D are. Now this could also be written as the matrix equation A, B, C, D multiplied by the column vector V1, V2 equals 7, negative 42. And I'll just say note this. And this is solvable, uniquely solvable, if and only if this matrix A, B, C, D is invertible. Now all this we know. Now let's go to specific examples. I want to give this as kind of an overview of linear transformations in R2. And of course, if we went to R3, we could have a V1, V2, V3. We'd have to have, well, we could have anything over here. It could be 2, 3 dimension. We're not going to worry about that at this point. But we could extend this to higher dimensions. And we would just end up with more components, more equations, and a different matrix. This matrix might or might not be a square matrix. If it's a square matrix, then you have a unique solution if and only if it's invertible, and all the stuff that we already know about. Okay, well, that's what we mean by a linear transformation. This is a general form of linear transformation in R2. Any linear transformation in R2 will have this form. You just have to give the numbers A, B, C, and D. And any linear transformation in R2. Now when I say in R2, from R2 to R2. Okay? So transforming a vector in R2 to a vector in R2, and then everything can be set up as a matrix in this way. Now, we're not going to talk too much about the matrices today. We're just going to talk about linear transformations, images, and preimages. So I'll just introduce that notation. This vector we regard as the image of the vector v1, v2. Okay, our solution v1, v2 here would be the preimage of the vector w equals 7, negative 42. So write that in something that'll show up a little better. Our solution v1, v2 is the preimage of w equals 7, negative 42. So we have image and preimage, and that's what we want to look at.